Let's switch in English. I'm very happy to welcome Andrey Sibirev today from Dropbox. This guy is just amazing. It's a great speaker. And today his challenge is to present the whole infrastructure of Dropbox in 40 minutes. So let's go, Andrey.
Hello. You hear me right? So, yeah, I'm going to try to chat about how we run things in Dropbox. I'm going to try to pack it up in probably even 30 minutes so that we have some time for questions in the end. So, the initial idea for this talk was to chat about the one team in the company that I work for, and the team is called Bedrock. And it's called that for a reason, because this is the team that is responsible for the bedrock of Dropbox, which is the way we run things, the way we provision servers, the way we deploy services, the way we build things and stuff like that. And then I figured out that probably the best way to actually talk about this is to talk about a lifetime of a service, which is we just pick some newborn service and try to follow its way through Dropbox infrastructure from its inception in the heads of developers or managers or whoever, and until its death. And I've been told that fin is death in French. So let's start from the infancy. So once the idea is conceived in the heads of some people in the company, they start to work on it. They start to develop the service, write in some of the languages that we have in the company, and probably the most important thing that happens in this life is when they try to build it first, right? And see if it works or not. Run some tests, stuff like this. So for builds, and I think building and testing is probably more important than actually deploying, because if you can't build and test things properly, there's just nothing to deploy. For builds, we use Bazel. So I'm going to chat a little bit about that. So Bazel is another thing from Google. It's an open source project. And if you go to its website, it will claim that it's a build system and it's supposed to make things better for organizing your builds and stuff like that. But I'm pretty sure that it's actually not a build system. It's more like a religion. And it's a religion because there is only two ways. You either do things Bazel way or you just die. That's it. Nothing works otherwise. It's a gigantic pain in the ass. It's really hard to actually do that, but it comes with a lot of benefits, and it's for the greater good. And the main benefit that we have from using this is that we have 100% USDA certified, hermetic, and repeatable, reproducible builds. It's really hard to achieve without a system like that, because you have to enforce a lot of rules, you have to talk to people and make sure that they do good things and follow best practices and they don't do anything bad. And with Bazel, there's just no other way. They just have to do it this way. We use monorepo, so basically we have one Bazel that manages almost all the code in Dropbox. So if any developer wants to build a service and wants it to run, these people have to use Bazel for that. And they have to write a build file, and this build file will have to specify all dependencies for the service explicitly. It doesn't matter if it's a library from Dropbox, library from some third party, or some data file, even an image, a picture, JPEG, anything like that. It has to be explicitly specified. And because this is the case, we have the full dependency graph for everything in Dropbox in one place. After the build is done, we want to run some tests, obviously. So for that, we use Docker, like probably everyone else in the world. So all the local builds, all the tests, everything runs in Docker for us. And we use one well-defined root file system for all this, and we have one well-defined runtime profile. We're going to chat a little bit about this later, but it's important that we have these both things well-defined. And yeah, we'll talk about this later. And the third important part of our, let's call it development infrastructure, is the commit queue. So the idea behind commit queue is that basically if a developer, if an engineer, SRE, or whoever who works with the repository wants to learn code, this code has to pass the commit queue. Commit to is like this very paranoid gatekeeper in front of our repository. And this paranoid gatekeeper is responsible for automatically choosing all the tests that have to run before the code can land. And so first of all, this is actually a compliance requirement for us. We cannot do it otherwise. But the other important benefit from this is that we know that our repository always builds and always works. There's no broken code in it because it just cannot land. I think that's quite important property to have. The tests that run by this paranoid Android are chosen automatically based on the dependencies that Bazel detected from the build files and based on the code itself. So I think I can say that we have a main language in the company, but probably we use Go and Python equally, and we have a little bit of Rust. So for Golang, it's really easy to do this because it's statically analyzable. We can extract all dependencies from the code itself. We know what's happening there, what kind of things you import and stuff like this. So for Golang projects, for Golang services in Dropbox, we basically know everything about the code, so we can determine exactly what tests to run based purely on the commit itself. We don't need anything else apart from that. For Python, it's a little bit harder. For Rust, it's just some black magic, so we don't really know what to do with it yet. But we'll figure that out, I guess, later. So Bazel files for builds, Docker for testing, and a commit queue as a gatekeeper in front of our repository before you can even land the code into the repo. But once it's done, it's time to deploy things, at least to try it out in production. So I think this basically outlines the infancy of a service: test, build, test again, build, test, and then at some point, maybe you arrive at a time when you actually want to deploy a service into production. So I call this adolescence because it's not really adulthood yet. Probably doesn't work. Probably it will break something. Maybe, hopefully not. But let's chat about this. This is a little bit more interesting. So basically, with the development infrastructure we have, with the reproducible builds, with hermetic builds that we have thanks to Bazel, and with this fact that we can be more or less sure that the code that we are going to deploy is probably 99% working because of the commit queue, we can move forward to this interesting concept that emerged recently in the world of SRE, which is immutable infrastructure. As in, if we know that the build is reproducible, which means basically it doesn't matter where you build, doesn't matter how many times you build, this will be the same artifact all over again, byte to byte, we can make interesting assumptions about infrastructure in general. So one thing we can do is that we can pretend that this code will never change once it's deployed. Sorry, it's my alarm clock. Still in New York time. We can pretend that this code will never change and the service will never change in production as well. So one important step towards this is, first of all, making sure that the server fleet that we're going to deploy our stuff to is also immutable. So what we want to see in production is that all the services are the same. This is like the ideal world that we want to be in. All hosts are absolutely the same. There is absolutely no difference. It doesn't matter where we deploy things. Of course, in reality, it doesn't really happen this way. For example, we have different hardware classes. Some hosts have more memory. Some hosts have better disks. Some hosts have more cores and stuff like this. But in general, it's just this gigantic cloud of servers that we don't really care about. There is this famous saying in the SRE world that your server fleet have to be cattle, not pets. So we're trying to get there. We're not there yet, but we're moving forward. And if we have this assumption that all servers are the same, a good outcome of this is that if something happens to a service or to a server, and it can be something bad like hardware failure or network going down, something like that, we can just forget about it. We can just recycle it and move the service somewhere else. But we also can do the same thing when the server is not actually in a bad condition. For example, if we over-provision services or if some alert is firing, the general idea is that we just recycle it anyway. I know that a few years ago in my previous jobs and stuff like that, we used to kind of trying to nurture server back to life. I think some people are actually familiar with this. Like you see that the server is dying and you SSH to it and you look at top and you look at this, look at logs and like, what can I do to make it kind of come back to life? We don't do that. If it's dying, we just shoot it in the head and that's it. We can provision a new one. That's a very good way of actually doing things. I really like it. Even though it sounds a little bit violent, it actually helps us move forward faster because we don't need to care about the single instances of failures. Of course, if a failure is spanning multiple servers, we'll look into it because something is definitely wrong, but this one-off cases about things misbehaving, we don't even really care about why they misbehave, just shoot them, that's it. Another thing I wanted to chat real quick about is the configuration management. And the metamorphosis that is happening to configuration management, at least around the places I work, is very interesting because I guess about 10 years ago, CM was like a thing that would save us all, and now what I see is that CM is the thing that's going to kill us all. So in Dropbox, at least, we think that configuration management is actually a bad thing, and we don't want it around us. Chef, Puppet, and whatever else is actually not a thing that we want to use. And the main reason for this is because in the long run, all configuration management systems, Chef or Puppet or whatever, they end up being these huge unmaintainable messes of arbitrary bash scripts that run on your machines at random times. When you start with infrastructure, you want to use Chef or stuff like that because it simplifies provisioning, but eventually it just ends up being at this point where it's just unmaintainable. And there are some reasons for this. One reason is probably because it's just really hard to test Ruby for normal people. Another reason for this is because it's really easy to write rules in Chef and Puppet that just run bash scripts, and a lot of people do that. So what you get eventually is just this sort of arbitrary SSH root access by a robot into your computers that just run stuff because nobody knows why. So we still have it around, and sometimes there is no way from using it, so we still have it, but we really try hard to make sure that it's not there anymore. And we're trying to converge on the model from CoreOS, where you just provision your machine as an immutable image, and that's it. You just basically mount rootfs and run from it, preferably read-only. And then comes this. This is a very elaborately named system at Dropbox that is supposed to take care of all deployments and everything in our infrastructure. I don't know actually why it's called yet another push system, because I've never seen another push system in the company. I think that's the first one. But anyway, this is the thing that basically has a real-time view of everything that's going in production right now. It knows all about all the servers, it knows all about all the services, it knows all about dependencies, all about the actual things that run on the servers, because it also replaces init and stuff like that. And this is where it all comes together. This is where developers and SREs actually interact, right? Because this is where developers specify whatever they want to run, their artifacts from the build system. They specify the configurations, the binaries, the command line switches and stuff like this. And this is where SREs, I'm an SRE by the way. This is where SREs actually make sure that this all makes sense and works. So yeah, artifacts, how to deploy, which is basically a thing that is coming from service owners, where they specify the number of replicas they want for a service, the specific hardware configuration, if they want like some special servers with more memory or bigger disks for storage, for example, and stuff like this. And how to run, which is the runtime environment configuration. I'm going to talk about this later. But first, before that, let's talk about the actual packages that we deploy. The idea here is that because we strive to have immutable infrastructure everywhere, and we basically want to have as much immutable pieces in infrastructure as we can, because in the long run, it helps us to keep less variables in mind and to better predict outcomes of disasters and actually sort of simulate disasters better to be ready for them. So one of the important pieces of this idea of immutable infrastructure is the packaging, right? Because if you just rsing things around into your immutable service, it's not really immutable. It's not really servers, I guess, as well. So for file systems, we just take the basal artifacts, which we know that they are hermetic, and we know that they're reproducible, so we don't really care about like which build box built them, or we don't care about if we build them today or tomorrow or yesterday. We just take whatever, because we know these properties of them, and we pack them into SquashFS file systems. The, I guess, important property of SquashFS is that it is read-only by design. You just cannot change it. The only way to mount it is read-only. If you try to mount it read-write, it will just not happen. So we take these artifacts that are produced by Bazel, and we just pack them into these file systems. And then we upload it to a package store, which is like a service that's supposed to keep all these things for deployments. And because we have a lot of servers, I'm not actually allowed to tell you how many servers we have, but we have a lot. Because of that, every deployment becomes a stress test, more or less. And it actually depends, because some services just needed to be deployed on a few boxes, but some global services, maybe we have, I don't know, 100 of them or something like that. They have to be deployed everywhere, and that's a stress test for the network infrastructure. And at some point, the network engineering team just told us that they just cannot take it anymore. They're just going to quit if we continue doing this. So we started to use torrents for this. And apparently, torrents are not only good for piracy, they are also good for deployment and copying a lot of things around in infrastructure. So the package store that we have is basically a gigantic torrent tracker inside the company that we use to develop, to deploy legitimate things. No movies and stuff like this. The next part is that the package that we have as a result of a build is not enough to actually deploy things. We also need the second package, which is the configuration, which is the way we're gonna actually deploy things, right? And for this, we also use code, which is a really good idea, I think. So we have a special Python DSL that I'm gonna show you later. And this Python DSL is supposed to let engineers, the service owners themselves, to define what is gonna happen with the service once it hits production. And this code belongs to the same repo as the code itself. So they just basically kind of stay around to each other. And because of that, the most important consequence of this is that this is also guarded by the same commit queue, which means that you cannot land the configuration for your production infrastructure without passing the commit queue. And because it's all built with Bazel, we know exactly what your code depends on. And because of that, we will not land code, the configuration code, that will somehow damage other services. And we know that before even starting the production, before even running the code, we already know what's going to happen, because we already know what it's going to touch upon. We already know what it will affect because of the dependency graph and because of the commit queue. So this gives us a certain degree of confidence that the thing that we're deploying probably works and probably won't ruin everything around it. But I still can't do that, of course. I'm just going to show you a few examples of how this DSL looks like. I'm not going to take a lot of time because it's just boring code. But basically, if, for example, we have a code piece that a service that is called awesome.d, this is how it looks like. It's just basic Python with a few things that DSL defines, like program or kick. Just to explain a little bit, the first block here, what it does basically is it defines a new program, which is the minimal unit of things that we can run. It just defines the command line for this thing and probably another very important thing about this is the runtime config, which is the profile. This is how we're going to run things in production. This is the contract between us as the people who run things and service owners as the people who write things, right? So we'll have some time for questions after that, and we can chat about this more. I can actually show how it works in the actual production. But the basic idea here is that it defines a profile, which is like a collection of defaults about things like how to start things, what security primitives to use, what container configuration to use and stuff like this. It can define a little bit of customizations for people, like we want to mount this special, for example, HDFS volume from the host and stuff like this. And a little bit more of security primitives as well. And the second part of this, the second block, is the kick, which is basically a collection of programs. This is the minimal unit of things to actually run. If the program is the minimal unit that we can operate on in terms of infrastructure, a kick is a thing, it's like a bundle of programs basically that we have, that we can run as one. And this is the rest of it. Basically, this is how we define a build. And because everything in Bazel is just like one giant repo, we can have a build that defines, for example, the daemon and also the CLI tool for it. And that's going to be the single build. And because it's a single build, we know that the CLI is the same revision as the daemon, and there's probably not going to be any problems with compatibility between these two things. The second block here is how an engineer can define deployment. Deployment is the actual unit that's going to land on the server and going to run there. And the deployment is where you combine build and kick, which includes all the programs, and also specify the allocation specification, which is how, where it's going to run. In this case, it's just ID is one of the data centers. We want 8 replicas of the service. And runtime dependencies. In this case, some internalization libraries and stuff like this. And it just all boils down to this project definition, which is like just basically a set of deployments just for a logical organization of things in the company. So yeah, runtime profiles. Basically, this is the only place where we directly interact as people who run production with people who write services. We don't actually need to interact with them in any other way. And we try to confine this to a very minimal set of things. So basically, like if you look at how many options you can specify to a program in Docker, for example, just look at the Docker like -- help. There's like 3 pages of things. So nobody really understands, I guess, what it means, and nobody really wants to bother with specifying all of them. So we took the liberty away from our engineers a little bit here, and instead of 3 pages of options, we have like 4 options, not pages. And apparently that's enough. Nobody really wants to care about complex stuff. Everybody wants to just run things faster and better, and that's it. So this is the contract that we have with other engineers in the company. They tell us we want to run it this way, and we tell them, yeah, we'll make sure that this is the thing that we will do for you. And yeah, that's just a screenshot of how the Yaps thing looks like. This is like some example. Basically, this is the UI that probably engineers see all the time when they try to deploy something in production. So after the talk, I can show you this thing live, but this is very simple. You can build things, you can push things. Kick means basically restart things, and you can roll it back. And it tells you where it runs, it tells you the revision, the package ID, stuff like this. There's not a lot of fancy stuff. And also you can obviously see that we don't really have designers on the team. But yeah, this gets to the point where service is up and running, but that's not enough, because this is where it all starts to come apart, as usual. This is the adulthood, the hardest part of life. And we, as SREs, we just want things to be deployed once and never change ever again at all. And we want engineers to just be able to deploy things once in their lifetime and then never touch it again. But this never happens. And what usually happens is that it all works until this point, and then it all just breaks. This is the point where we actually have to deal with reality. And this is the funniest part of the job, I guess. So how do we do that? How do we make sure that things don't break, or don't break that often? So I guess the first thing that we have to do is to have more containers, because containers contain things. If a thing breaks in containers, it's just that. If a thing breaks outside of container, it probably touches more things, and things start to fall apart faster and in a worse ways. So yeah, that's a very nice quote that I really like, that I think applies to a lot of things in life, but to software engineering and infrastructure and site reliability engineering especially. Yeah, we must all suffer from one of two pains, the pain of discipline or the pain of regret. And we definitely don't want to suffer from the pain of regret. So we just want to kind of suffer for other engineers, let's put it this way, so that they don't have to. So right now we have about 1/3 of all the services in production in containers. And this move started, I think, a year ago, like a year and a half ago. Before that, there was actually no containers at all. And we want to have about half of production in containers by the end of the year, but it is not an easy journey for us, because Dropbox is, 10 years old? So there is a lot of things in production already that just been built even before containers even happened. There are services that just assume that containers never existed. And these services are not something that you can just throw away and just forget about it. And we cannot rewrite them either. So it's kind of not that easy. And because there was a lot of existing infrastructure in the company already, we couldn't just take Docker, for example, and use it in production right away, or Rocker or whatever. So we had to take something simpler than that, so that we could integrate it with the existing infrastructure in an easy way. So we went like 2 levels below, and we actually use the run C directly in production instead of Docker or Containerd or anything like that. And it's fine, because this is the thing that powers Docker and Kubernetes, for example. And it has all the same features, they just exposed in a different way. And because it doesn't have a lot of things on top of it, like Docker, for example, we could integrate it easy with the rest of our existing infrastructure, like, for example, the package management system or deployment system and stuff like this. Like, for example, we don't need to use the Docker registry because we have our own registry, sort of, with torrents and stuff like this. And we don't need to use the way, like the Docker image approach with multi-layered images, because everything is immutable and our artifacts, the build system artifacts, are reproducible and hermetic. So we just collapse all these images into one big immutable image and put it into our package store. So because of all these things, we didn't really need, and we really couldn't use all these ready solutions with all these extra features. So we just built everything on top of run C. Another thing that we have is pipelines, which is our way to move fast, like Facebook does, but without breaking things. The idea here is that the engineers can use the thing that they use every day anyway, which is Git. But in this case, it's not really Git. They can use direct acyclic graphs. They can define the way their services are going to be deployed in production step by step, where each step can be anything from, like it says here, from posting a message to Slack, or maybe posting like a fancy box with a button to Slack where they can click things to ask for permission from the team, or to start metrics, or actually more things than that. For example, to run a load test on a canary, or to do some RPC call to some third party, let's call it, service that would determine if the deployment should proceed or not. And that's a very powerful system, actually, because without it, you have to keep in mind all these things for big deployments, like, I don't know, canary staging, testing, stage deployments and stuff like this. With pipelines, you don't actually need to do that, because you just define it once and then just sit and click in Slack, and that's it. That's very easy. And actually, the first version that we built didn't have any automation, because we thought that people, the other engineers, they will be, how to say that? They will care about how good it, like how the actual deployment happens. So we added these features to have explicit permissions. We added these features to monitor things and whatever. But I think a month after this feature was deployed, we had, I think, a few teams right away that just built auto-clicker for it. Just click through deployment as fast as possible. So at some point we just, okay, well, apparently they don't really care. The thing that this makes the system good is that because, again, of all these things with Bazel and dependencies and dependency graphs and commit queue, we can make this system deterministic and safe because it already knows what's going to happen. It already knows what code is going to be deployed. It already knows what this code depends on, what services it will depend on. Because the configuration is also code in the same repo behind the commit queue, the system knows what's actually going to happen during the deployment. And because of all this knowledge, it is quite intelligent under the hood, even though it looks very simple on the outside. And it allows us to automate more things and spend less time in front of a computer, which is a good thing for all of us. And the last thing, probably the most interesting, is Nauru. I've been told that it is healer in Japanese, but I don't know for sure. The idea behind this is that no matter how hard we try to build an immutable infrastructure, no matter how we try to make sure that every piece of the infrastructure, every piece in the pipeline is immutable, read-only, and stuff like this, there still be things that change. There still be things that introduce these little bits of entropy here and there in the system, which can be as simple as just a failure of the hardware, like we just cannot protect against this. Or some maintenance of the network, for example, because it has to happen. You have to reconfigure routers, so you have to move links around, stuff like this, and it will cause some chaos in the system. This can be a bit more complicated, like, for example, there is some bug in the code that we didn't catch, and it manifests in some weird conditions, and it happened, and the process started to crash and stuff like this. So when left unconfined, this entropy will result in chaos, and if we don't actually do anything about it, then at some point, this chaos will just consume the whole infrastructure and everything is gonna just die. So we've built this system, which is, initially it was a auto-remediation system similar to foobar by Facebook, which is basically consume a Nagios alert, try to match it against a bunch of regexes, and if a match happens, then there is a action to take based on that. So in the easiest example, it's something like hardware failure detected, recycle the box, stuff like this. But eventually, over time, this system developed into something more than that. And at this point, this is more like a, how to put that? It's like a anti-entropy machine, which is pretty cool. The idea behind the current version of this is basically that everything that we need to happen in production, not right now, will happen through this system, which is, for example, as an example of something that has to happen right now is deployment. Like if a developer clicked a button to deploy things, it has to happen right now. But things like, for example, during the deployment, we determined that a few boxes have some issues with one of their disks in the RAID array. It's not something that has to be fixed right now, but it is something that has to be fixed at some point. And we just make a note in Nauru saying that this has to be solved at some point. Like we have to recycle this box eventually after the deployment is done, which is something that has to be done right now. And this system will take care of it. And it has a bunch of rate limits and all the checks and waits to make sure that it doesn't do anything stupid. So it kind of is very slowly paced system that just takes care of production over time, but it probably took care of 95% of system administrator work in the company. I can't remember the last time I was looking at Nagios dashboard at this point. This is the Nagios alert administrator bot as well, I guess. So given these three things, this is basically enough for us to keep our production relatively safe. And this takes us to the death. This is the last thing I wanted to talk about. And the idea here is that every time I hear a talk like this about like things in companies around deployment, development, testing, production, everybody's talking about how we build these super new exciting services and amazing products and I don't know, like grocery shopping blockchain apps and stuff like this, and how we're going to push into production and deploy it and people will use it and everybody will be so excited. But nobody talks about these old, services that already serve their purpose and they have to go away, they have to retire gracefully, but nobody really cares about this. So I just wanted to spend like a minute talking about this because this is very important. If you think about it, we just cannot move forward without retiring these services. If we build a new exciting way of doing a thing A, it will not work until the old exciting way of doing thing A is no longer in production because you just cannot have two things at the same time. And this is the part where I've seen the most pain in infrastructures today, I guess, is deprecation and retirement of all services. This is just not covered by any of the existing systems. It's not happening. We just kind of pretend that they don't exist anymore. And it works maybe in 33% of cases, but in 66% of cases, you have weird artifacts popping out all around the production at some point, where you have sort of a new system was already coming in, but the old system is still kind of there a little bit, and sometimes it kind of pops back to life and does some action, and it just destroys everything, and everybody's like, what just happened? Well, this would happen. Take care of your old things. And yeah, to start thinking about retirement today, and stay away from computers. It's bad for health. That's it.
Thank you very much, Andrey. Challenge done. Thank you. So we have 5 minutes for questions. So if somebody have a question.
Yeah, feel free to ask about any part of these circles if you want.
Hi, thanks a lot. How Nauru, which is an anti-entropy system, is constrained to not add entropy? How do you make sure, for example, it does not step in when you have to do maintenance or troubleshooting?
So there are a few mechanisms for that. So first of all, when you define a new, let's call it a remediation, like an action set for some condition, you have to define constraints for it as well, which are rate limits, the host limits and stuff like this. So you cannot just say that if this happens, just do it everywhere. You have to say, if this happens, do it on this set of hosts with this space, with these limits. Another thing, which you just asked about what happens, or what we could do to make sure it doesn't intervene with like ongoing stuff like that, right? Is there are two ways to do this. One way is to use the banning mechanism, which is like you can tell it that on this subset of production, you're just not allowed to act on this subset of conditions. Like you can say that, for example, we know that this block of servers have bad disks for some reason, but we just cannot deallocate them because there is, for example, nowhere to relocate the services, or we just don't care about these disks. You can just ban a remediation. You can tell it, no, just don't do this on this subset of services for now. Of course, all these kind of things, they have another check on top of it, as in like if some engineer banned a remediation, then eventually, I think after like a few hours, it will start to alert us because it shouldn't actually be a thing that just stays in production for a long time. So there's sort of like a two-layer kind of thing here, basically. One engineer bans remediation to do some maintenance work, for example, but then it will start to emit another alert that can trigger another remediation, or it can alert us. So I don't know if it answers the question, but basically, yeah, there's like a lot of mechanisms around it to make sure that everything is safe. Basically, yeah, probably the most important part about Nauru is that we want it to be safe to run, let's put it, overnight when everyone is asleep.
Any other question? We have time for one other question.
Damn, I did a really good job explaining. Oh no, I did not.
Yeah.
I guess, understand, you do not use Docker?
We use Docker for testing. We use
Okay.
Docker for development infrastructure.
Yeah.
We don't use Docker itself in production. We use runc, which is a part of it,
Yeah.
but we don't use the actual Docker binary.
Uh,
Maybe
ac-
yet, I
Actually,
mean-
I mean for packaging, you do not use Docker.
For packaging,
Yeah, like packaging and images.
yeah.
You choose to use Bazel, that's right?
Well, we use Bazel for builds itself.
Yeah.
Bazel is like, let's put it, it's like a very good replacement for Make.
Yeah.
And for packaging of these artifacts that are the result of these builds, we have an in-house solution for this,
Okay.
package store, right? So basically we take the artifact, we put it into a squashfs file system, which is a read-only image. Then we put it into our registry with torrents.
Okay.
And then we use it to distribute it to the service that's
So
supposed to run it.
wha-
We just download the file system and just mount it directly on the host.
Okay. So it's because it didn't exist at the time you start it, or do you have some regrets about custom solution? I mean, versus layering of Docker, so something like that.
So when package store started in Dropbox, I think it was like 2010 or something like that.
Okay.
So back then, if Docker existed, it was like beta 4 or something like that.
Okay.
So, but then again, I think, so I work in Dropbox for a year. Actually, today is my anniversary, 1 year. So when I joined, there was some opportunities, I would say, to actually try to introduce it into production, but we didn't do it because everything already works.
Okay.
So why break things that work? That's like the worst advice we can have.
Yeah, that's true. Okay.
Last one.
I see as well that you have some kind of Python in order to control the start of your service. Why don't you just use something like systemd or supervisor in order to start the service that actually run on your servers?
So we actually do use systemd because there is apparently no other way in the world right now. But we use systemd to start like the basic foundational services on the host, like, I don't know, let's say like bind and stuff like this that just don't make sense to start without things. But one of the things that systemd starts is our own init that is responsible for starting the Dropbox services. And the idea behind it is that we have a bunch of Dropbox specific things that just are not in systemd. And we have a very good integration between our init system and the rest of our observability infrastructure, like logging, monitoring, metrics, and stuff like this. So basically, this was like, I guess, that happened before me, so I'm not really sure how it happened exactly, but the idea was that instead of having systemd running like as a generic runner for everything, and then try to distinguish between this is our services that we know how to monitor, and this is not our services that we don't know how to monitor, or like we monitor with something else, like here is our things and here is Prometheus, let's say. We have systemd that runs whatever everybody is familiar with, and our init system that runs our stuff, and it knows that it's our stuff. So it knows that it can connect to this specific port, get metrics from it, and stuff like this.
Thank you very much, Andrey. Please applause again. Thanks.